Welcome back to my course. Today we're going to be talking about linked lists. So, what is a linked list? A linked list is a fundamental data structure used to store a collection of elements dynamically. Unlike arrays, linked lists do not require a contiguous block of memory. Instead, they use nodes, where each node stores a value and reference to the next node in the sequence. So there are multiple types of linked lists. The first one would be a singly linked list, where each node has a pointer to the next node. The second type would be a doubly linked list, where each node has two pointers, one to the next node and one to the previous node, and a circular linked list, where the last node points back to the first node, forming a loop, which will not be talked about in this course. Linked lists allow for efficient insertion and deletions in comparison to arrays. Now, let's talk about a node. A node is the building block of a linked list. Each node consists of two primary components. One, the data, which is a value stored in the node, and the pointer, or the reference, which is a link to the next node in the list. For a doubly linked list, a node includes an additional pointer to the previous pointer, showing traversal in both directions. Nodes are allocated dynamically in memory, making linked lists a flexible data structure for efficient memory management. Now, how do you insert a new node? Inserting a new node in a linked list requires adjusting the pointers to maintain the sequence. There are different insertion scenarios. So let's say you're trying to insert at the beginning. Well, the new node's pointer would be set to the current head, and the head reference is updated to the new node. If you're trying to update it at the end, then the list is traversed until you find the last node, then its pointer is updated to reference the new node. And if you're trying to insert it at a specific position, the list is traversed to its desired position, and pointers are adjusted to insert the new node without breaking the sequence. In contrast to arrays, linked list insertion does not require shifting elements, which makes it efficient, particularly for large datasets. Time complexity varies. It is O to the 1 for inserting at the head, O to the n for inserting at an arbitrary position, or at the end. Now, let's look at how to delete at the head node. So, deleting the head node is not a simple operation, but it requires careful pointer management. First, you would like to store the reference to the current head node. Then, you would update the head pointer to point to the next node in the sequence. Then, you would free memory allocated to the deleted node. For doubly linked lists, an additional step is required, which is that you have to update the new head node's previous pointer to null. This deletion operation runs in O to the 1 time, making it highly efficient. Now, let's look at the length of a linked list. To determine the length of a linked list, we traverse the list while maintaining the count of nodes. The process follows these steps. The first step is to initialize a counter to 0. Then the second step would be to start from the head, and you would iterate through each node, incrementing the counter at each step. Finally, you would stop when the end of the list is reached, and you would return the counter value. Since this approach involves visiting each node once, the time complexity is O to the n, where n is the number of nodes in the list. Now let's talk about a doubly ended list. A doubly ended linked list has two references, one to the first node and one to the last node. With the first node is known as the head, and the last node is known as the tail. This structure allows for two things. Firstly, it allows for fast insertions and deletions at both ends. Unlike singly linked lists, where inserting at the end requires traversal, doubly linked lists maintain direct access to the last node. And the second thing that this structure allows for is efficient queue implementation. Queues require constant time enqueue or insertion and dequeue deletion operations, which doubly linked lists support efficiently. Doubly ended lists provide flexibility in managing elements dynamically, improving performances for use cases like caching and task scheduling. Now, let's look at a doubly linked node. So a doubly linked node extends the functionality of a singly linked node by including three things. It includes the data, which again stores the node's value. It includes the next pointer, which points to the next node in the sequence, which was also in the singly linked list. And however, this also contains a previous pointer, which points to the preceding node in the sequence. The presence of both these backward and forward nodes, it allows for two things. It allows for bidirectional traversal, which means you can navigate in both directions, and efficient deletion, as removing a node now does not require traversal from the head. However, the trade-off for this flexibility is increased memory consumption, as each node requires additional storage for the previous pointer. Despite this, doubly linked lists are widely used in applications such as browser history tracking, undo and redo functionalities, managing LRU, which is least recently used caches. Understanding linked lists and their variations is crucial for efficient memory management and optimizing dynamic data handling in software applications. That's it for this video.